Tonight, we're going to explore one of the most uncomfortable questions in human spaceflight. Could you actually survive an entire year on Mars? At first, the answer seems obvious. We already know how to keep people alive in space for months at a time. We've built space stations. We've lived aboard them for nearly a year. So why should 1 year on Mars be any different? Because Mars isn't just another place to live. It's another planet. Every hour you spend there, the environment quietly pulls your body farther away from the conditions it evolved for over billions of years on Earth. The longer you stay, the less forgiving the planet becomes. What feels manageable after a day isn't the same after a month. What seems survivable after a month isn't necessarily survivable after a year. That's the question this video is really about. Not whether humans can reach Mars, but whether they can still be healthy, functional, and alive after living there for 8,760 continuous hours. By the end of tonight, you'll understand why surviving a full year on Mars is one of the greatest biological and engineering challenges humanity has ever considered. What slowly changes inside both the human body and the systems keeping it alive, and why simply making it to Mars may turn out to be the easiest part of the mission. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. You are standing on Mars. Not imagining it, not watching footage of it, not reading about it from a warm room. You are there. And the first thing Mars does is nothing dramatic. It does not erupt. It does not shake. It simply sits. And the air around you quietly begins to kill you. The surface pressure on Mars is around 600 pascals. Earth's sea level pressure is around 101,000 pascals. That is less than 1%. Not thin air, like the summit of a mountain. Not uncomfortable air, like a high altitude plateau. Near vacuum. The kind of pressure differential that your body cannot negotiate, cannot adjust to, cannot survive inside for more than a handful of seconds. Without a sealed, pressurized shell around you, your lungs cannot transfer oxygen to your blood. The difference in pressure is simply too large. But that is not even the first thing you notice. The first thing you notice is that the saliva on your tongue starts to boil. The moisture on your eyes does the same. Not because it is hot, because the pressure outside is so low that liquid at body temperature cannot stay liquid. It vaporizes. Your body, without that suit, is just a bag of fluids in the wrong environment. You have around 10 to 15 seconds of useful consciousness. Then, the brain runs out of oxygen and shuts down. Not slowly, not with warning. 10 seconds. 15 if you are lucky. The suit is not optional gear. It is not equipment. It is your skin, your lungs, and your pressure shell all at once. Remove it, and Mars does not need to do anything else. But here is where it gets strange. Even if you could somehow compress the Martian air and breathe it, it would still kill you. Because the air itself is wrong. Mars's atmosphere is around 95% carbon dioxide. Oxygen makes up only a trace. Earth's air is around 21% oxygen, with nitrogen filling the rest as a stable buffer, and the human body is tuned to exactly that ratio. Breathing compressed Martian air is not like breathing thin air. It is asphyxiation inside a toxic low-pressure bath of CO2. So every breath you take inside a Mars habitat is manufactured. It does not come from outside, it comes from machines. Pumps pull in the outside gas. Compressors raise the pressure. Scrubbers pull the carbon dioxide back out. Oxygen generators and tanks feed clean oxygen into the loop. Several machines running together, producing the air one breath at a time. You breathe the output of a system, not a planet. And that system can drift. This is the part that does not make it into most conversations about Mars. When people think about the danger, they think about a seal blowing out or a meteor punching through a wall. Those are real. But the more insidious failure is slower. Habitat pressure drops a few kilopascals. CO2 creeps up by a couple of percent. Nothing alarms, nothing sounds. You start to feel a headache, then tired. Then your thinking slows. Your reactions get sluggish. Your judgment softens. On Earth, if the air in a room feels stale or close, you open a window. On Mars, there is no window to open. The outside is not usable. The only fix is more hardware, more maintenance, more attention. And the cruel part is that slow CO2 buildup and gentle pressure loss produce exactly the state of mind in which you are least able to notice warnings. least able to run diagnostics, least able to catch the problem before it compounds. The air degrades your judgment at the same moment it degrades itself. That pattern will come back. It comes back through every system on Mars. Small, unnoticed drift, compounding quietly until the moment it cannot be ignored. Remember it here, because the air is where it begins. Now add cold. The average surface temperature on Mars is around negative 63 degrees Celsius. That is negative 81 degrees Fahrenheit. At night, it falls past negative 100 degrees Celsius, negative 148 degrees Fahrenheit, colder than the worst days recorded in Antarctica, by a wide margin. Cold does something that is easy to underestimate. It does not just feel bad. It changes what things are made of. Metals contract and pull against their fasteners. Plastic components turn brittle. O-rings, the small rubber rings that seal every joint and coupling, harden in cold. A hardened O-ring does not seal the way a flexible one does. It sits in the groove. It looks intact, but it no longer conforms to every variation in the surface around it. It leaks. Lubricants that keep mechanisms moving thicken and eventually freeze. A valve that worked perfectly in testing does not work the same way at negative 90 degrees. Your habitat wall holds a comfortable interior, around 20 degrees Celsius, against that brutal cold. Every joint in that wall, every seam, every bolt, is being stressed by that difference constantly. Continuous heating costs kilowatts of power, every hour, every night, every soul. Lose power for even a few hours, and the interior temperature begins to fall. Batteries weaken as they cool, which means they produce less power, which means the heating weakens further, which means the temperature falls faster. Water freezes in pipes and filters. The body loses heat faster than clothing alone can compensate. The base, the warm, manufactured space that was keeping you alive, becomes a cold survival problem in its own right. And then there is the sudden version. Inside your suit or inside the habitat, the pressure is near Earth normal, tens of thousands of pascals against 600 pascals outside. That difference is a force constantly pushing outward through every seal, every visor, every weld. If a helmet cracks, if a visor shatters, if a seal fails at the wrong moment, that pressure difference vents in an instant. Eardrums can rupture. Moisture on the tongue and eyes boils again, just as it would on unprotected exposure. The lungs cannot push air out against the pressure gradient, cannot scream, cannot cough. Useful reaction time is measured in seconds, not minutes. Survival in that moment depends on how quickly the breach is isolated and pressure is restored. Automatic shutoff valves, backup compartments, emergency masks, practice drills, all of it done in bulky gloves, in a cramped space, tired, cold, stressed, possibly in the early stages of hypoxia. The planet does not have to attack. It only has to wait for one seal to fail at the wrong time, which brings the final weight of this section down onto a single number. A Martian year is around 8,260 hours. Every one of those hours, every joint, every O-ring, every weld, every patch, every window is holding that pressure difference, fighting that cold, sustaining that manufactured air. On Earth, a micro crack in a seal is a maintenance note. You add it to the list, you fix it next week. On Mars, a micro crack slowly bleeds your air into a near vacuum until either the rate becomes detectable or the moment arrives when that joint fails completely during an EVA. Build a base and live there. That is how people describe it. What it actually means is build a life support system that cannot fail in an environment where failure is the default condition and keep it running without interruption for 8,760 hours. The air alone is enough to end year one. And the air is only where the story starts. Suppose you hold the air. Suppose the seals stay tight, the pressure holds, and the manufactured atmosphere does its job every hour of that first year. You can win the fight for air and still be losing a quieter one. Because there is a kind of damage that does not stop at the wall. It walks straight through the habitat, straight through your suit, straight through you. On Earth, you never notice it. The planet wraps itself in a magnetic field and a thick column of atmosphere, and together they deflect or absorb most of the high-energy particles streaming in from the sun and from the wider galaxy. You live under that protection your entire life, and it never once registers. It is invisible precisely because it works. Mars does not have that field. Its global magnetic field is essentially dead. Its atmosphere is thin enough that the particles come straight in, and the numbers that follow from that simple fact are not alarming in the way a breach alarm is alarming. They are alarming in a quieter, slower way. On the Martian surface, the baseline radiation dose runs roughly 0.2 to 0.7 millisieverts per day. A millisievert is a measure of absorbed radiation and the biological damage it is likely to cause. A few millisieverts over a year is fine. A few hundred raises your cancer risk in a meaningful, medically documented way. A few thousand is immediate acute danger to organs and tissues. On Earth, you absorb about 3 millisieverts in an entire year from background radiation. On Mars, you can absorb that same yearly dose in a couple of weeks. A full Earth year of radiation, compressed into 14 days. A 1-year stay on the Martian surface, even with reasonable shielding, can easily bring your cumulative dose to a few hundred millisieverts. That number sits in the range where your cancer risk is measurably, permanently elevated. Not science fiction risk, medical risk. But the reality was different. A few percent higher cancer risk does not sound terrifying on its face. It sounds like an acceptable cost. What you cannot see is what that number means at the cellular level, because at the cellular level, it is not a statistic. It is continuous, invisible, ongoing damage. Ionizing radiation, the kind that comes through your habitat wall, knocks electrons off molecules and breaks chemical bonds. When a high-energy particle passes through a cell, it can break the strands of DNA. Not one strand. Sometimes both at once. Your body has repair systems, and they work most of the time. They patch most of the breaks, but they miss some. And sometimes they rejoin the broken ends in the wrong order, mismatching the code. Over months on Mars, you are hit again and again. Each hit carries a small probability of a mutation that the repair system gets wrong. Most mutated cells die. Some do nothing, but a few, over enough iterations, can acquire the ability to ignore the signals that tell cells when to stop growing. That is how tumors begin. Not all at once, not with a moment you can point to. Just a quiet statistical accumulation, cell by cell, while you feel nothing. You feel nothing. That is the part that sits uncomfortably. Your risk is being rewritten, silently, while you check instrument readings and eat your morning meal. The slow version is frightening enough. Then there is the fast version. The sun is not a steady source. It erupts. Solar flares and coronal mass ejections throw intense bursts of high-energy particles outward at enormous speed. On Earth, the field and atmosphere turn most of that aside. Astronauts on the International Space Station have advance warning, quick support systems, and the possibility of evacuation. On Mars, a major solar particle event can spike radiation by orders of magnitude over the already elevated background. Not a modest increase, orders of magnitude. The dose that normally accumulates over days arrives in hours. The defense is mass. Meters of Martian soil piled over a shelter. Thick tanks of water positioned around a safe room. Enough material between you and the sky to absorb the burst before it reaches you. If the shelter is well designed and you are inside it in time, you survive the event. If the shelter is underbuilt, you take a serious dose fast. If you're in the middle of a long spacewalk and the event arrives before you can return, you take it outside, in a suit, with almost no shielding between you and the particle stream. Acute radiation sickness is nausea, vomiting, profound fatigue, immune collapse, damage to organs. On Earth, it is a hospital emergency. Intensive care, specialized treatment. On Mars, there is none of that. A small medical kit, perhaps one doctor, and whatever can be improvised from what you carried. No evacuation, no escalation to a higher level of care. Whatever you have is what you have. But the threat does not stop at your body. This is the reveal that most people miss. Radiation is not only a health problem, it is also a hardware problem. And the hardware problem can kill you just as quietly as the cellular one. High energy particles flip bits in electronic memory. A 0 becomes a 1. A 1 becomes a 0. Silently. Instantly. In most computing environments, this is a nuisance. Error correction handles it. But your life support systems are computers. They drive pumps, valves, and sensors. They run the software that monitors CO2, manages pressure, controls thermal systems. A particle that hits the wrong chip at the wrong moment can corrupt a sensor reading, freeze a control loop, or skip a safety check. Think about this. It is 3 in the morning. You are asleep. A cosmic ray passes through your habitat and hits the controller chip inside the CO2 scrubber. The software jumps. A safety check is skipped. The scrubber quietly shuts down. But the scrubber's reported values do not change. They still read normal. The alarm system is tied to those reported values. Nothing triggers, nothing sounds. CO2 begins to climb, slowly. Over hours, you wake groggy, your head aches, you think you slept poorly. The air around you feels fine. The numbers on the panel say everything is normal, and the gas mix is already sliding. That scenario is not hypothetical in its mechanics. Single event upsets. The technical name for these bit-flipping events are a documented phenomenon in space electronics. Mission designers account for them, build redundancy around them, use radiation-hardened components where the cost can be justified. But hardening costs mass. Redundancy costs mass. Every kilogram launched to Mars carries an extraordinary price in fuel and logistics, so there is constant pressure to trim. To decide that this level of shielding is probably enough, that this component can use the standard version instead of the hardened one, and that is usually the right call. Until one day it is not. Radiation will probably not kill you within year 1 outright. That is not its pattern. Its pattern is quieter and longer. Over 12 months it chips at tissues and at gear. Every spacewalk adds to your cumulative dose. Every solar event eats into your remaining health margin. Every uncaught flipped bit is a potential life support glitch that either gets caught by redundancy or doesn't. You may reach the end of year 1 still walking, still functional, still capable, but the damage in your body and in your systems is already there. It does not reset at the 12-month mark. You do not start fresh. You carry what accumulated. The air was the first problem. This is the second. And the threats have only just begun to stack. Radiation rewrites you from the outside in. The third threat works from the inside out, and it does not even feel like a threat at first. It feels like a gift. The moment you step onto the Martian surface, you weigh less. A person who weighs roughly 150 pounds on Earth weighs something closer to 57 pounds on Mars. Mars pulls at about 3.7 meters per second squared, which is roughly 38% of what Earth's gravity delivers. A 70-kilogram body reads about 27 kilograms on a scale. Walking feels lighter. Jumping feels effortless. Carrying equipment that would grind you down on Earth suddenly feels manageable. The crew members who have trained for years in full Earth gravity will feel, for the first time in their lives, something close to a physical superpower. But that is not what is happening. That lightness is your first big physical downgrade. Here is the mechanism. Your bones and muscles do not maintain their strength out of loyalty to you. They maintain it in response to load. Stress the skeleton, apply force, demand output, and the body keeps the structure. Reduce the load, and the body concludes the structure is no longer necessary. On Earth, your skeleton and muscles work constantly, every waking moment, just to hold you upright and move you through 1G of pull. On Mars, the load signal drops by more than half. The body takes note. Bone tissue begins reabsorbing its own minerals, especially calcium, redistributing them away from the skeleton because the skeleton has sent a clear signal that it no longer needs quite so much. Muscles lose fibers. The heart, which on Earth maintains a careful output, calibrated for the effort of pumping blood upward against full Earth gravity, gradually relaxes. Blood vessels adjust. Everything quietly scales down to match the environment it now lives in. And you feel fine. Better than fine. That is the problem. The clearest numbers we have come from astronauts on the International Space Station, living in full microgravity. They lose roughly 1 to 2% of bone mass per month, even with strict daily resistance training and treadmill sessions built into their schedules. Mars is not full microgravity, so the rate of loss is somewhat better. But somewhat better than 1 to 2% per month, over 12 months, is still an enormous structural change. The exact Mars-specific number is genuinely uncertain. We do not know it precisely. What we do know is that you are removing more than half the normal skeletal load, day after day, without pause. The habitat having a gym does not stop the physics. The physics operate whether you are exercising or sleeping or repairing a broken sensor at 2 in the morning after 6 hours of difficult EVA work. Which brings in the heart. In low gravity, the cardiovascular system recalibrates. Blood does not pool in the lower body the way it does on Earth. The heart relaxes its output. The vessels adjust their tone. This is fine while you're lying down or moving slowly and steadily. But when you stand up quickly, blood can still drop toward the legs faster than the recalibrated system can compensate. Blood pressure falls. The brain briefly receives less oxygen than it needs. You feel lightheaded. In a worse moment, you black out. On Earth, you sit down, put your head between your knees, wait 30 seconds, and you're usually fine. On Mars, a significant portion of your standing and moving happens inside a rigid EVA suit with limited visibility, carrying tools on terrain that is uneven and sometimes loose. Blacking out in that suit can mean a hard fall, helmet into a rock, a twisted suit joint, a glove scraping an edge. Any of these can escalate quickly. A cracked helmet ring is an air emergency. A torn glove is an air emergency. And this particular air emergency began not from equipment failure and not from a radiation event. It began because your legs could not handle a stumble in weak gravity. Something else was happening. The gravity is also sending minerals from your dissolving bone into your bloodstream and eventually into your urine. That is the chemistry that builds kidney stones. On Earth, kidney stones are brutal. Sudden, severe pain in the back or side, nausea, blood in the urine. Miserable. But on Earth, there is an emergency room. There is imaging, there is pain management, intravenous fluids, procedures to fragment or remove a stone that will not pass. On Mars, there is a small medical cabinet and possibly an ultrasound if the mission carried one. A stone small enough to pass will still require managing severe pain in a person who may be scheduled for a critical maintenance task tomorrow. A stone large enough to fully block a ureter is more dangerous. The blockage builds pressure. Tissue gets damaged. Bacteria have somewhere to grow. Infection can spread from the urinary tract into the blood. That is sepsis. On Earth, sepsis means an ICU, intravenous antibiotics, and surgeons. On Mars, it means you, a small formulary of drugs, and a margin that is already thinner than you would like. Now add the suit. A Mars EVA suit with its backpack life support system and a set of tools can exceed 100 kilograms of mass. That is more than 220 pounds of equipment. Mars gravity reduces how much that weighs, but it does not reduce how much it masses. Mass resists being started. Mass resists being stopped. A stumble while carrying that much inertia through uncertain terrain means you do not just catch yourself the way a human body does when walking light. You pitch forward into momentum. And the body trying to catch that momentum is a body that has been losing bone density, losing muscle fiber, losing coordination in its cardiovascular response for 6 months, 8 months, 10 months. The gap between what the brain thinks the body can do and what the body can actually control widens with every passing month. The brain still has the muscle memory of a fully conditioned, Earth-trained crew member. The body operating inside the suit is quietly a different thing. Not weaker in any way that feels obvious, not painful in any way that demands attention, just a little less stable, a little less able to absorb the unexpected. And the unexpected is constant on Mars. You must have strict gym schedules. Every mission plan includes them. They help. But you are also working long hours. Maintenance, scientific observation, habitat repair, EVA preparation and recovery, equipment diagnostics, and the ordinary emergencies that arise whenever complex systems operate at the edge of their specifications. Sleep deprivation is nearly certain. Stress is nearly certain. And in that context, skipping one workout becomes skipping two. Skipping two becomes a pattern. The physics never take a day off. 0.38 G is 0.38 G whether you are disciplined or exhausted. This is what the body's first year on Mars actually looks like. Not the heroic poster, not the triumphant crew planting a flag in strong, capable bodies. The story underneath is a bent curve. A fall in month 1 is a bruise. The same fall in month 10 lands on bones that have been losing density for nearly a year and snaps something. A brief power cut in month 2 leaves you cold and shaken, but functional. The same power cut in month 12, with a cardiovascular system that has been recalibrating for low gravity work for 12 months, with blood pressure control that has grown slower to respond, might push you to the edge of losing consciousness in the cold. Getting used to Mars and losing the robustness you arrived with are not two different things. They are the same process. The gravity that felt like a superpower on landing day is the same gravity that has been quietly unbuilding you from the inside ever since. 3 threats have now settled into the body, and the one that arrives next does not come from the environment. It comes from the planet's biology, or rather its absence of one. While your body quietly weakens, the planet is already working its way inside, not waiting for a catastrophic moment, not announcing itself with a single dramatic event. It enters through the seams of your suit after every EVA, settles into the filters of your habitat, and drifts through the air each time an airlock cycles. The 4th threat is not a force that strikes you. It is material. It is the ground itself. On Earth, dust is an annoyance. You wipe it off a shelf. You brush it from your jacket. On Mars, the dirt is one of the primary reasons you do not survive year 1. And the first thing to understand is what it actually is. Martian regolith is not beach sand. Beach sand has been tumbled by water for millennia, its edges worn smooth, its grains rounded and relatively harmless. Martian regolith has never touched liquid water in any meaningful way. It is crushed rock, raw, fractured angular fragments with edges that cut. Many of those fragments are only a few micrometers across. A human hair is roughly 70 micrometers in diameter. These particles are many times smaller than that. At that size, they behave more like a gas than a solid in some respects. They stay suspended in even thin Martian air for extended periods. They ride on every movement, every breath, every swing of an arm, and they slip into gaps that seem impossibly small to contain them. Low humidity and constant friction give the particles an electric charge. They cling, not loosely the way ordinary dust settles on a surface you can wipe clean. They bind electrostatically to suit fabric, to visor glass, to cable insulation, to the rubber of seal gaskets, to the joints of gloves, to the faces of tools, to the panels that collect your power, to the fins that reject your heat. You walk back in from an EVA and you carry the planet with you. You brush the suit. You run a vacuum over it. Some of the regolith releases. Some does not. Some is already embedded in the fabric fibers. Some has found its way into corners of the airlock, into the gap between the helmet and the collar ring, into the ventilation pathway. Every EVA adds to what is already there. The contamination is cumulative. It does not reverse. We have seen a version of this before. Apollo astronauts reported that lunar dust smelled like spent gunpowder, scratched the visors of their helmets, stiffened the joints of their suits, and irritated their lungs and eyes after only a few days on the moon. A few days, and they came home. Mars dust is similar in size to lunar dust, but it is more chemically active, and you are not there for a few days. You are there for months. The short visit escape does not exist on Mars. But something was wrong. The chemical activity of Martian regolith is not just an abstract concern about reactivity. It is a direct threat to your food and your water. Martian soil contains perchlorates. These are highly oxidizing salts, the kind of compound that does not belong inside a human body in any significant quantity. They occur in Martian regolith at roughly 0.5% to 1% by mass. That sounds small. It is not small when you consider what a kilogram of soil carries, or what happens when that soil gets into your water supply or your growing system. Perchlorates interfere specifically with how the thyroid gland uses iodine. The thyroid regulates metabolism, temperature control, and energy balance. Disrupt it and you are silently twisting another knob against a crew that already has very little margin. Long-term perchlorate exposure is linked to increased cancer risk and endocrine disruption. This means any system that brings Martian material into the closed loop has to treat that material like chemical waste. You cannot fill a greenhouse bed with raw Martian dirt and grow food in it. You have to strip it, wash it, heat it, or abandon it entirely, and bring your own growth media. Water that passes through Martian soil must be chemically processed to remove these salts before it enters the drinking supply. Even washing a suit that came in from outside becomes a controlled chemical operation. One badly filtered batch of processed water, one small leak in a regolith washing line, and the vegetables carry a low dose of a hormone-disrupting compound. Not an obvious dose, not one that causes immediate symptoms, one that quietly presses on a narrow health margin, day after day, for months. The particles that reach your lungs cause a different kind of damage. Bigger particles are caught by the nose and upper airways and cleared by the body's normal defenses. Micrometer scale particles are not. They travel past the airways and reach the alveoli, the tiny sacs deep in the lungs where oxygen passes into the blood and carbon dioxide passes out, and they tend to stay there. The lungs respond with inflammation and scar tissue. On Earth, long-term inhalation of mineral dust causes silicosis and related diseases, collectively called pneumoconiosis. The symptoms build slowly: chronic cough, shortness of breath, chest tightness, eventually respiratory failure. On Earth, a specialist can image the damage, slow the progression, and manage the symptoms. On Mars, there are no lung specialists. There is no advanced imaging. There is a limited formulary and a crew who need every unit of lung capacity they have when something goes wrong. Think about what lost lung capacity actually means in that environment. Climbing a ladder inside the habitat becomes noticeably harder. Suit work outside becomes a sustained physical effort, and emergencies demand exactly the capacity that has been quietly consumed. Early symptoms, fatigue, and a mild cough are easy to attribute to other causes: sleep deprivation, stress, the general physical load of the mission. By the time the symptoms are clearly respiratory, months of irreversible scarring may have already accumulated. The dust does not stop at the body. Every mechanical system faces the same relentless abrasion: airlock hinges, suit joint bearings, rover wheels, pump shafts, valve seats, fan blades, all of them exposed to micrometer-scale abrasive fragments every time a door opens or an airlock cycles. The grains work their way into lubricants and transform them into grinding paste. Metal wears against metal. Seals erode, joints stiffen and draw more power and fail earlier than their design specifications suggested. Solar panels accumulate a coating of settled dust that reduces their output. Radiator fins collect a layer of fine material that impairs heat rejection and risks electronics overheating. On a nuclear-powered system, panel efficiency matters less, but you still rely entirely on mechanical systems to move air through the habitat, pump water through your processing loops, regulate temperature, open hatches, and drive the rover across terrain where being stranded is not an inconvenience. A stuck valve in a cooling loop means overheating. A jammed rover wheel means stranded. A failed airlock latch means a door that will not seal or will not open. Not a maintenance ticket. A direct threat to your ability to reach shelter. The real verdict on dust is not any one of these effects. It is that none of them operates alone, and none of them stops. From the first day, dust enters every imperfect seal, every gasket that is slightly below perfect tolerance, every gap between components that only exists because the engineering had to make trade-offs. Filters clog and require replacement. Brushes wear. O-rings grind down faster than lab testing predicted, because the real Martian environment is harsher and more variable than any chamber on Earth. Every EVA adds contamination. Every moment of fatigue that leads a crew member to skip a full cleaning cycle because it is late and the next task is already overdue lets more of the planet into the bubble. By the end of the first year, dust has found every shortcut. Airlock cycles are rougher. Suit joints are looser. Pumps are noisier. Power output is lower. And lungs have been absorbing fine mineral particles for 12 months. There is no single dramatic dust event in this story. No movie climax storm that builds to a decisive moment. The real danger is a rising background of wear, contamination, and subtle biological damage, until one day a pump fails earlier than anyone expected, or an airlock seal gives out during a storm, or a crew member with lungs already carrying months of accumulated inflammation develops a respiratory infection they cannot shake. Dust does not kill in one blow. It pushes every mechanical and biological system a little closer to the edge every single day until something important finally slips over it. And that is still not the full picture of what the Martian environment does to everything you depend on. Of all the machines that the dust and the cosmic rays and the cold are quietly wearing down, one stands apart. You can lose a rover wheel and survive. You can lose a solar panel and reroute. But there is one system that cannot slip even for an afternoon, cannot be paused for repair, cannot wait until morning. It runs every second of every day, making air where there is none and removing poison where it builds. It is the machine you are living inside, not on Mars, inside a machine that pretends it is Earth. And that machine must never, ever turn off. Think about what that means in practice. Air, water, temperature, humidity, and waste are all handled by hardware running continuously around the clock, for 365 days. Every breath you exhale goes somewhere. The carbon dioxide is stripped out, the water vapor is condensed and reclaimed, the oxygen is replenished. Nothing vents to the outside. Outside is near vacuum and toxic. The loop is closed, and it stays closed, because opening it even briefly means trading the inside of a machine for the inside of a coffin. On the ISS, if a scrubber fails, a replacement ships up within days. If the situation is serious enough, the crew returns within hours. That net exists because the ISS is roughly 400 kilometers above the Earth. Mars is tens of millions of kilometers away, depending on where the two planets are in their orbits. A resupply mission takes months to plan, launch, and arrive. A return trip is not guaranteed at all, so the closed loop has to work. Not well most of the time. Perfectly, all of the time, with no outside help. That is the only version of this that ends with people still alive. The answer was stranger than expected. The first failure mode inside that loop is not explosive. It is not loud. It does not announce itself. Carbon dioxide builds quietly. At around 1 to 2% concentration in the air, the effects begin. Not unconsciousness, not panic. Just headaches. Grogginess. A little trouble concentrating. Decisions that come slightly slower than they should. At 1 to 2%, there is still plenty of oxygen in the air. CO2 itself, at that level, is the problem. And here is the trap at the center of it. The gas making you less sharp is the same gas you need to be sharp enough to fix. If CO2 continues to rise while you are already impaired, you can pass the point of safe recovery before you have fully understood what is wrong. At 5 to 8%, panic and confusion set in. Above that, unconsciousness. If it keeps rising, death. And the warning before all of that is just feeling a little off today, a little foggy, a head that aches in a way that might be sleep deprivation or dehydration or the stress of a long week. Scrubbers keep CO2 in range through sorbent canisters, materials that chemically bind CO2 as air passes through them. The canisters saturate and must be regenerated or replaced on a schedule. Valves have to open and close in the right sequence. Fans have to keep pushing air through the system. Sensors have to read accurately. If a cartridge is left in too long, if a valve sticks, if a sensor drifts and underreports, the CO2 can begin to rise without a single alarm sounding. There is no loud event, just the air, changing slowly, in a room where everyone is slowly becoming less capable of reading the instruments clearly. That is not the only gas the loop has to manage. Oxygen has to come from somewhere, and tanks alone cannot last a long mission. The most likely production method is water electrolysis. Run an electrical current through water, split it into hydrogen and oxygen, feed the oxygen into the habitat air, and manage the hydrogen separately, venting it, storing it, or using it in another chemical process. On paper, it is straightforward. In practice, it means hardware handling high-pressure reactive gases around the clock in a cold, dusty, radiated environment. Electrolyzer membranes can tear or clog. Catalysts degrade over time. Seals and fittings endure constant pressure cycling, expanding and contracting with every temperature shift. And the gases involved are not forgiving. Oxygen aggressively supports fire. Hydrogen is flammable and its molecules are small enough to leak through gaps that would stop almost anything else. On Earth, a fault in an electrolysis unit means shutting down, venting safely to the outside, calling a maintenance team, and evacuating the building. On Mars, that unit feeds your lungs. There is no safe outside to dump a problem. A leak, a spark, and an oxygen-rich pocket mixing with hydrogen in a closed habitat can end everything in seconds. So the system needs multiple redundant tanks, pressure relief valves, instant fire detection, and suppression capability, because there is nowhere to run and no crew that arrives within the hour. The word redundancy sounds like a solution. It is also a problem. Every backup scrubber, every spare membrane, every redundant oxygen generator, every extra sensor and valve and filter adds mass. Launch cost runs into the thousands of dollars per kilogram across the full mission architecture. Mission planners work from spreadsheets where every additional kilogram of life support hardware means less mass somewhere else, more launches, or a mission that simply cannot be funded. So the pressure to shave redundancy is constant and rational. 3 scrubbers or 2 with spares, a full duplicate oxygen generator per module, or one shared between sections. How many replacement filters for 12 months of continuous operation? These decisions compound, each one reasonable in isolation. The result is a system where you are one crucial device, short of full redundancy, exactly when a failure occurs early. Not two spares, one. Not a full backup unit. A few critical components. Enough margin to feel manageable in a spreadsheet. Not enough margin to feel comfortable when something goes wrong in month 4. And things will go wrong. The question is never whether a component fails. It is which component fails first, and what else is happening that same day. A part rated for a mean time between failures of 5 years looks safe on a 1-year mission. Most of those units will last well past 5 years. Some will fail much sooner. Add Mars to the equation, and Earth lab numbers become something closer to optimism than engineering. Temperature swings drive expansion and contraction through every fitting and seal. Dust works into every mechanism that moves. Radiation bit flip sensors and control software. Constant cycling wears seals that were tested in clean labs at controlled temperatures for limited durations, not run around the clock in a dirty, cold, irradiated environment by tired humans who are already carrying months of physical and cognitive wear. Year 1 on Mars is not operating a life support technology in a known environment. It is stress testing it in conditions it has never actually seen. A scrubber shuts down from a software fault during a dust storm. Power is already tight because panels have been dimming for weeks. The oxygen generator is underproducing because a water pump is partially clogged. Humidity is climbing because a condenser is running behind spec. None of these is a catastrophic failure on its own. But the loop is a system. Each variable affects the others. CO2 climbs a little. Oxygen supply drops a little. Humidity rises a little. Temperature starts to drift. What were engineering margins on a whiteboard become life or death boundaries on Mars. And once the loop slides out of specification in more than one variable at once, pulling it back without making things worse becomes extremely difficult. Fixing one system draws power that another system needs. Rerouting airflow to push CO2 through a working scrubber changes the humidity balance. Every adjustment in a closed loop touches everything else. Which component fails first is genuinely unknowable. That is not a failure of planning, it is the nature of the problem. The machine that is keeping you alive is also being subjected to Mars, continuously, for the first time. And the rest of the threats have not stopped stacking while it runs. That oxygen machine has an appetite, and what it eats is the hardest thing on this planet to get out of the ground. Water underlies almost everything happening inside that habitat. The CO2 scrubbers need it to function. The electrolyzer that makes your oxygen needs it as feedstock. The plants need it. The crew needs it for drinking, for rehydrating food, for washing wounds, for keeping infection from gaining a foothold in a place with no hospital. On Earth, water is background. You turn a tap and the question of water simply does not arise. On Mars, that feeling disappears on day 1 and never comes back. Water becomes a number. A number watched the way you would watch a heart monitor in an intensive care unit, because a wrong trend in that number has no backup planet behind it. Think about what that number actually has to cover. On Earth, one person uses roughly 50 to 70 liters of water a day without thinking. That is 13 to 18 gallons, spent on drinking, showering, flushing, dishes, and laundry. On Mars, that pattern dies entirely. Usage is cut to a few liters per person per day. Showers become a wipe down with a damp cloth and a small bag of warm water. Nothing is wasted. Almost everything is recycled. And even at that level of ruthless rationing, a crew of 4 or 6 or 8 still needs tons of water cycling through the system over a year because the demand is coming from so many directions at once. Drinking, food rehydration, washing, plant irrigation, air humidity, oxygen generation. The loop is large. You cannot shrink it past a certain floor without systems starting to fail. You cannot bring that water from Earth. Launching liquid water costs thousands of dollars per kilogram, and even a minimal mission water supply runs to multiple tons per crew member. The math closes that option before it opens, so the water has to come from Mars. The picture did not hold. Mars has water. Scientists have known this for years. There is ice at the poles. There are buried deposits under the regolith in many regions. So the resource exists. But knowing it exists and having it in your tank are two completely different things. The water is not a lake. It is not a surface block you can melt. It is ice-locked in frozen ground at roughly negative 60 degrees Celsius, which is negative 76 degrees Fahrenheit, or colder, mixed into the regolith as permafrost, layered in buried deposits that require excavation to reach. Getting it out means running an industrial cold mining operation on another planet. You excavate regolith, you move it to a processing unit, you heat it until the trapped ice vaporizes, you capture that vapor, you cool and condense it back into liquid. Every step in that chain requires hardware. Excavators, drills, augers, industrial heaters holding precise temperatures, condensers, pipes that must not clog with dust or ice over in the cold. All of it running in low gravity, low atmospheric pressure, and extreme temperatures, with power limits that do not flex. If the drill jams, the chain stops. If the heater elements burn out, the chain stops. If vapor lines ice over and block the flow, the chain stops. And at that point, the water resource is just a colored patch on a scientific map. Not in your tank, not in your system. The crew falls short of their assumed daily liters, and the margin begins to shrink. A few weeks of shortfall shrinks it fast, and even when the chain works, what comes out is not clean. The water extracted from Martian permafrost carries dissolved salts, microscopic mineral particles, and in many areas perchlorates, the same oxidizing compounds already in the dust. Every liter requires treatment before it can be used. Filtration to remove particulates and fine metal fragments. Distillation or chemical processing to strip out salts. Possibly reverse osmosis, forcing water through special membranes under pressure to remove what other steps miss. Each of those stages uses membranes, cartridges, and pumps that can clog, foul, or degrade. The purification system is not passive, it wears. Poor filtration does not announce itself loudly. What it does is quietly let extra salts through. Extra salt stresses blood pressure control and strains the kidneys, a problem that compounds against bone minerals already leaching into the bloodstream from low gravity. Perchlorates that slip through disrupt thyroid hormone production, impairing metabolism and long-term endocrine health. Microscopic metal particles accumulate in tissues over months. None of these effects present as a single dramatic event. The crew member feels tired, headaches, cramps, electrolyte levels drift. The natural assumption is workload, sleep disruption, mission stress. The actual cause is a purifier slipping quietly below specification while the readout says everything is fine. Not an obvious warning, not a sudden system alarm. A slow accumulation of bad chemistry in every cup of water, every day. Now add the quantity problem on top of that. The total water in the habitat loop is a clock. Every liter is accounted for. What is in storage? What is circulating? What can be reclaimed from air humidity, from urine processing, from grey water, from the mining operation? The loop has a budget, tracked to the liter, because every liter lost shortens operating time before the crew hits a wall they cannot push past. A leak of 1 liter per day sounds trivial, less than a large bottle of soda. But over a year, 1 liter per day is 365 liters gone. That is roughly the volume of a large home aquarium. Annoying on Earth. On Mars, it is a significant fraction of your entire usable buffer, gone with no way to quickly replace it. And leaks are not always dramatic. A hairline crack inside a wall panel dripping into insulation, unseen for months. A valve not fully seating, venting slow vapor into an unrecovered section of the habitat. A flow sensor calibrated in Earth conditions reading full while the tank level quietly drops. The sensors are the eyes, and sensors drift. They were calibrated in a lab. Mars is not a lab. Wait. The sensor says full, but the tank is dropping. By the time the discrepancy becomes obvious, the buffer is already smaller than the mission plan assumed, and there is no water truck to call. Refilling means throwing more energy into the mining heaters and hoping the hardware holds another cycle. If production drops and losses rise simultaneously, the crew faces a choice that has no good answer. What do you cut first? Reduce personal hygiene to conserve water, and infection risk rises in a closed environment with no hospital. Reduce irrigation for the food plants, and crop output weakens, increasing dependence on finite packaged rations. Reduce the water fed to the electrolyzer that makes oxygen, and the breathing margin shrinks. You are choosing between cleanliness, eating, and breathing. Each cut has a price. Each price is paid immediately, by real people in a small sealed space, with no way to trade between mission phases to smooth the shortfall. Mars does not need to attack. It just sits dry and cold while the heaters run, the purifiers clog, the sensors drift, and the tanks trend slowly downward from design values. One unreplaced filter cartridge, one miscalibrated flow sensor reading normal during a deficit, one hairline drip behind a panel, and the sustainable base becomes a place where every cup of water is a number someone argued about. The water system has to work, continuously, accurately, without significant loss, for the entire duration of the mission. Whether in situ extraction actually meets the assumed daily liters, under real Martian conditions with real hardware wear, remains genuinely uncertain. That question does not resolve on a whiteboard. It resolves on Mars, with a crew inside, while the clock runs. And the other systems that water feeds have not stopped running while that question is being answered. Follow that irrigation water one more step, into the greenhouse, and the margins get tighter still. On a short mission, you live out of packets. Calorie-dense, carefully formulated, sealed in foil, launched from Earth with every nutrient already measured in. For a week, 2 weeks, a month, that plan works. For a year, it collapses under its own weight. Not figuratively, literally. One person's food for a full year runs into the hundreds of kilograms once you count packaging, water content baked into rehydrated meals, and enough variety to keep a human being nutritionally complete. Multiply that across 6 crew members, and you are looking at several tons. Several tons to lift out of Earth's gravity well, accelerate across interplanetary space, decelerate into Martian orbit, and land without destroying it. The rocket bill becomes impossible. So the pressure shifts. Instead of bringing all your food, you grow it. Greenhouses, hydroponic racks, maybe algae tanks running alongside the rest of the closed loop. You arrive on Mars as mission specialists. Within weeks, you are also farmers, systems engineers, and lab technicians, managing a living food production operation in one of the most hostile environments in the solar system. And if you get any part of that wrong, it does not show up immediately. It shows up on your plate a few months later. Mars does not help you grow anything. The sunlight reaching the Martian surface is roughly 43% of what strikes the top of Earth's atmosphere. Dust cuts it further on bad days. The temperature outside the greenhouse would kill a plant in minutes. And the soil? The actual Martian regolith you might imagine using as a growing medium is loaded with salts and perchlorates. You already know what perchlorates do to a human body. You do not want them in your food supply. So you build a controlled environment, artificial lighting or concentrated and redirected sunlight, carefully mixed nutrient solutions flowing to plant roots in hydroponic beds, air with tuned carbon dioxide levels, tight temperature control, humidity kept in a narrow band. The plants never touch Martian soil. Everything they need is manufactured, monitored, and delivered by the system you built and maintained. That is when the pattern broke. That system, the one keeping your food alive, is made of pumps, fans, LED arrays, valves, drip emitters, sensors, and controllers. Every single one of them now connects directly to your calorie count. A clogged nutrient line can wipe out an entire tray before you notice the flow has stopped. A blown power supply to one lighting bank throws a crop section into a wrong light cycle and disrupts growth timing by weeks. A software bug in the greenhouse controller floods a root bed, or lets it dry out overnight. Each small fault removes food you were counting on. Not food you might have liked. Food you planned your biological survival around. The delay between the fault and the consequence is what makes it dangerous. You fix the pump today. The crop it was feeding is already compromised. You find out at harvest. And even if everything runs perfectly, you are not finished. Because even a fully functioning food system on Mars runs a small menu. Humans need proteins, fats, vitamins, minerals, and trace elements in combinations that no single crop delivers. There is a persistent popular idea that you could survive on Mars by simply growing potatoes. You cannot. Not for a year. Not even close. Here is what actually happens when the crop mix drifts. Lose your leafy greens and you start losing vitamin C and vitamin K. That process is slow. You do not wake up one morning with scurvy. You wake up a little more tired than yesterday. Your gums bleed when you brush your teeth. A cut on your hand takes longer to close than it should. Wounds that would have healed cleanly start requiring more attention. By the time the connection is obvious, months of low-grade deficiency have already accumulated. Limited iron or vitamin B12 in the diet, and your red blood cell production slips, anemia sets in, and you run cold and fatigued at exactly the moment the work demands are not reducing. Drop zinc and your immune system, already compromised by radiation, loses another layer of defense and tissue repair slows. Each deficiency is quiet. Each one subtracts a little margin. And the crew is already running on narrowed margins everywhere else. The mental side is harder to see coming. Food is not only fuel. On Earth, even in difficult circumstances, you can vary what you eat. You can reach for something different when a meal feels unappealing. On Mars, the menu is what arrived on the ship and what the greenhouse produced this week. Months of the same rehydrated meals, the same few crops, the same rotation. There is a name for what that does to appetite: menu fatigue. You look at food with no real interest. You eat just enough to get through the next few hours, or not quite that much. Undereating creeps in without anyone announcing it. Weight drops. Muscle mass, already under pressure from low gravity and high workload, falls faster. Mood follows. In a small crew sealed inside a pressurized structure on a cold, dead planet, shared meals are one of the only normal human anchors you have. They are a pause, a ritual, a moment when the mission steps back and the people step forward. When food becomes bland, repetitive, or rationed, that anchor comes loose. People get irritable. Small frustrations feel larger than they are. Morale slides. And when morale slides, discipline follows. Maintenance steps get skipped because someone is exhausted and demoralized and tells themselves it can wait until tomorrow. Small problems get noticed and not logged because logging feels like one more demand in a day that has already taken everything. Those skipped steps and unlogged problems are exactly how small technical issues grow into serious ones. The food system and the crew's psychological stability are not separate concerns. They are the same concern, which brings the picture together in a way that is easy to miss until you see it whole. The food system does not have to fail completely to endanger the crew. It only has to underdeliver. A shortfall of 10 to 20%, fewer calories than the body needs each day, less protein, fewer vitamins, puts the body in a long, low-level deficit. You are burning more than you are taking in while simultaneously building and maintaining a habitat under constant physical and cognitive demand. Combine that deficit with bone loss from low gravity, muscle atrophy from the same, radiation damage accumulating in cells, occasional dehydration when the water system is stressed, and a workload that does not ease. The immune system weakens. Healing slows. Resilience drops. A minor respiratory illness you would shrug off in a week on Earth can knock you flat for 2. A small fall injury, the kind that produces a minor bruise in month 1, heals slowly in month 10. Slowly enough to risk infection. And on Mars, an infected wound, with a weakening immune system and a small formulary, is not a minor problem. By your first full year on Mars, if the agricultural loop and the stored supply have not matched what your body and your workload actually require, you are in biological debt. Not dramatically. Not obviously. The body is still making its payments. Bone strength, muscle repair, organ function, mental resilience. But it is making minimum payments it cannot sustain. Still standing at the 1-year mark. Still functioning. But the pantry is tighter than planned. The greenhouse has had emergency repairs. The crew is lighter, weaker, and more fragile than their medical files said when they launched. The curve is bent the wrong way. You are not failing. You are arriving at failure slowly, from a direction that looked like success the whole time. And the systems the food depends on have not stopped stacking their own pressures while the harvest comes in short. And there is one pressure you have not fully met yet, even though it has been present from the first sentence of this story. You have heard about the cold. The cold that turns O-rings brittle and freezes lubricants and steals battery power in a cascade. That cold is real, but the cold only tells half the story. The other half is heat you cannot get rid of. Think about what is happening inside the habitat at any given hour. Bodies generate heat. Computers generate heat. LED grow lights, water pumps, air circulators, power electronics, battery banks, heaters. All of them dump thermal energy into a sealed metal space that is, by design, cut off from the outside world. On Earth, getting rid of excess heat is often as simple as blowing air across a radiator or cracking a window. Neither of those options exists on Mars. The atmosphere outside is so thin, it barely carries heat at all. You cannot put a fan outside and let convection do the work. Space itself is a thermal vacuum. Heat only travels through it one way, as infrared radiation, glowing silently outward. So every habitat on Mars depends on radiator panels. Large flat surfaces mounted to face the sky, engineered to radiate thermal energy into space and keep the interior within its safe operating band. They work, but they are exposed to everything the Martian environment does to expose surfaces. Dust settles on them, not in thick drifts, but in thin, almost invisible films of electrostatically charged particles. A thin layer of dust does not sound like much. It is enough to drop thermal performance meaningfully, and it accumulates every day, the same way it accumulates on solar panels and suit visors and sensor lenses. Micrometeoroids and daily temperature cycling can bend or crack the panels themselves. Drifting regolith can partially bury them. Construction or new equipment can shade them. The reading came back reversed. The ground outside sits at roughly negative 60 degrees Celsius. By any ordinary understanding, that is an environment trying to freeze everything inside. But the electronics in the server racks, the battery arrays, the control boards, they can overheat. Not because Mars is warm, because the radiators meant to remove the waste heat the hardware generates are losing efficiency. Slowly, quietly, while the exterior temperature gives no indication anything is wrong. The outside is still trying to kill you with cold. The inside can still cook your equipment at the same time. Both are happening. Neither cancels the other. That is the first phase of the temperature problem. The second is older and slower. Every morning on Mars, the surface warms. Every night, it plunges back down. The daily swing is roughly 50 to 60 degrees Celsius, which is 90 to 110 degrees Fahrenheit. That cycle repeats tomorrow, and the day after. Over a full year, it repeats hundreds of times on the same bolts, the same composite panels, the same rubber seals, the same viewport glass, the same coolant pipe joints. Every material in the habitat expands and contracts at its own rate. Metals move differently than the composites they are bolted to. Plastics move differently than the metals they are sealed against. Sealants flex and relax. Glass accumulates tiny internal stresses. At first, nothing you can see. But over hundreds of cycles, the interfaces between dissimilar materials begin to show wear. Bolts work slightly loose. Seals warp just enough to sit unevenly. Hairline cracks begin inside coolant pipes, especially at bends and joints where stress concentrates. Viewport glass develops microfractures too small to see without magnification. None of this announces itself. Then, one cold night, a crack in a coolant line that had been growing for months opens wide enough to leak. Antifreeze, the fluid meant to carry heat away from sensitive components, begins to seep out. Or a seal that had been flexing slightly with every thermal cycle finally stops seating flat, and a slow air leak begins. Or a viewport fracture that was invisible at the last inspection becomes visible at the next one, and the question becomes how fast it is growing. Thermal stress quietly unbuilds the hardware around you while the temperature logs look normal. Now consider a threat that the cold and the heat did not bring from Mars at all. They carried it from Earth. In a sealed habitat, fire is among the worst events you can face. There is enough oxygen in a managed habitat atmosphere to burn plastics, fabrics, cable insulation, foam padding, battery casings, and circuit boards. All of those materials are present in dense concentrations. A shorted wire, an arcing connector, a lithium cell pushed past its thermal limit by degraded cooling, a heater that fails in the on position. Any of those can ignite material in a space where there is nowhere for fire to go that is safe. On Earth, the response to a building fire is to leave the building. On Mars, outside is unbreathable near vacuum. Rushing toward an airlock means donning a suit you may not have time to seal fully. Evacuation is not a default option. It is a last option, and a dangerous one. Fire suppression has to react fast, and it has to work on the first attempt. Inert gas flooding, water mist, foam, automatic power cutoffs. But every suppression method carries a cost. Too aggressive, and you displace enough oxygen that people in the same compartment begin to suffocate. Too slow or too weak, and the fire spreads into cable runs and insulation, releases toxic combustion gases, and begins damaging the life support hardware behind the wall panels. In the worst case, The decision becomes whether to vent part of the habitat to Mars's atmosphere to starve the fire of oxygen and save the rest of the base. That trade is fire for decompression risk. It is a choice no one wants and the environment can force. The temperature problem follows you outside as well. In the suit, in low pressure, on frozen ground, with thin air that barely moves heat at all, the suit must hold your body in a narrow thermal band, whether you are standing in shadow or working in direct sunlight. Most designs use a liquid cooling garment worn against the skin, combined with electric heaters and layers of insulation. If the heating system fails in the cold, the body loses heat fast. Fingers go numb, muscles stiffen, fine motor control drops. Within minutes, you are drifting toward hypothermia, which means a slowing brain, impaired judgment, possible unconsciousness. The analogy that fits is being dropped into an Arctic winter with no proper gear. Except your mobility is limited by the suit itself, your gloves are thick enough to make every movement deliberate, and your oxygen is on a fixed supply. You cannot sprint back to warmth. Every step toward the airlock is slower and heavier than normal. If cooling fails instead, the situation reverses. Working in sunlight, generating body heat from exertion, with a suit that can no longer move heat away from your skin, your core temperature begins to rise. Dizziness, impaired thinking, the early signs of heat stroke. You are inside a rigid shell. You cannot remove the helmet. You cannot shed layers. The environment that was trying to freeze you an hour ago is now trapping your own heat against you. And the condition that requires the clearest possible thinking is arriving at exactly the moment thinking becomes hardest. Temperature is not a background detail of the Mars problem. It is the referee quietly deciding which systems stay in the game. Too cold, and lubricants thicken, batteries lose capacity, water lines freeze, plastics crack. Too hot, and electronics glitch or burn out, seals soften and lose their shape, fires start, bodies go into heat injury fast. The safe middle band requires energy to maintain, hardware to monitor, and constant human attention to catch the drift before it becomes a failure. Over 365 days, the odds of passing through without a serious thermal incident are not favorable. A dust-fouled radiator that no one noticed until the equipment racks began running out of specification. Torn insulation creating a cold spot that slowly draws heat from a critical fluid line. A thermostat misset after a software update. Cycling a compartment through conditions that accelerate the exact thermal fatigue already accumulating in its seals and joints. Each of those is catchable if caught early, with the right parts and a crew operating with a full attention budget. But remember the stack. The same people managing the radiators and the insulation and the fire suppression are also managing their own bone loss, radiation accumulation, regolith exposure, psychological fatigue, water rationing, and a greenhouse that has needed emergency repairs. Thermal management is one more spinning plate. It does not fall by itself. It falls when attention slips. And attention on Mars is already spread thinner than any mission planner's whiteboard ever showed. The temperature problem has no single dramatic moment. It runs continuously in both directions, and the consequences of losing control of it touch every other system on the list. All of those spinning plates are being watched by one instrument that does not appear on any engineering diagram: the human mind, and it has its own safe band to fall out of. Every system covered so far, the air, the radiation, the bone loss, the dust, the life support loop, the water, the food, the heat, has one thing in common. A person has to notice it, respond to it, and keep responding to it correctly over hundreds of days. That person is not a sensor. That person is not a redundant module you can swap out. That person is you, and you are operating inside a small, repetitive, high-stress world that is actively wearing down your capacity to do the job. The uncomfortable question is this: when the planet is already wearing down the body and the machines, what happens when your own brain slides out of its optimal zone too? The isolation starts with distance, and the distance is not abstract. At closest approach, Mars sits roughly 54 million kilometers from Earth, about 33 million miles. At the far end of the orbit, it stretches past 400 million kilometers. Radio signals travel at the speed of light and still take between 4 and 24 minutes to cross that gap one way. Ask a question and wait 8 to nearly 50 minutes for an answer. By the time the answer arrives, the situation you were asking about has already changed. There is no real-time call to a ground specialist when a system behaves strangely. There is no quick conversation with a doctor when someone feels wrong. You record a message, send it into the dark, and wait. The problem in front of you does not wait with you. If something breaks badly, there is no one else driving. You are the adult in the room every time, whether you feel ready or not. That weight does not leave. It sits behind every decision, every shift, every moment you step away from a workstation to eat or sleep. The ground team is supportive, experienced, and unable to help you in real time. And that gap, that silence between message sent and message received, becomes part of the psychological texture of every single day. But here is where it gets strange. The isolation is not just about emergencies, it reshapes ordinary daily life in ways that are harder to point to. Your world shrinks to a habitat, some connecting tunnels, maybe a rover and a small outdoor work area. You walk the same tens of meters every day. Metal walls, screens, the same airlock, the same rocks visible through the same window. No forests, no cities, no crowds of strangers, no unexpected sound from outside. Only the constant hum of fans and pumps and electronics, and the knowledge that a few centimeters of composite wall separate you from an environment that kills in under a minute. The human brain did not evolve for this. It evolved amid varied sounds and colors and smells, crowds and animals and weather, environments that changed on a walk from one part of a landscape to another. Shrink that richness down to a few hundred cubic meters of recycled air and repeating corridors, and the mind pushes back. Days begin to blur. The boundary between Tuesday and Thursday dissolves. You feel stuck in a loop. Wake up. Check systems. Work. Dig. Eat. Exercise. Sleep. Repeat. Even if you love space, even if you chose this with every part of yourself, monotony works on you. It works on everyone. Now add the social reality. A crew of maybe 4 to 8 people, all depending on each other for everything. That sounds like a strength, and in many ways it is. But it also means no option to walk away. No ability to take a day from someone whose habits are grating on you. Every small thing gets louder in a closed environment. The way someone chews. The way they leave tools in the wrong place. The way they are always 5 minutes late to the morning briefing. On Earth, these are minor frictions. You walk away. You see different people on a different day, and the pressure releases. On Mars, that same face is at breakfast, at work, at maintenance, at dinner, and at the shared equipment rack where the two of you need to cooperate to fix the same valve. A disagreement over something as small as a checklist procedure can hang over a crew for days. And here is the part that raises the stakes in a way that has no Earth equivalent. The person you argued with this morning is the one checking your suit seals before your EVA this afternoon. That person might be the one pulling you back through the airlock if something goes wrong outside. You cannot afford a fractured crew. You also cannot manufacture goodwill under constant confinement. People respond by suppressing conflict to keep the peace, which builds resentment quietly over months, or by expressing it more sharply because there is no release valve anywhere in the system. The mental health risk is real, and it compounds. Less natural sunlight, filtered through windows and atmospheric dust and artificial grow lamps, can drift the circadian rhythm. Poor circadian rhythm degrades sleep. Chronic stress, the background awareness that any serious mistake can endanger everyone, means the underlying fear of failure never fully lifts, even off shift. Together, these conditions raise the risk of depression and anxiety in ways that matter not just for the person experiencing them, but for the mission itself. Depression is not just sadness. It is losing interest in things that used to carry meaning, feeling flat when you need to be engaged, struggling to motivate for tasks you have done correctly 100 times before, checking a filter, updating a log, inspecting a seal. Small things, necessary things. The kind of things that skipped once produce no consequence, but skipped 5 times across different systems begin to produce something serious. Anxiety pushes in the other direction, overreacting to small alerts, freezing when a fast decision is needed, interpreting ambiguous data as catastrophic, or ignoring clear warnings because the stress of responding feels unbearable. On a planet where small errors cascade into lethal situations in minutes, that mental drift is not a wellness concern in the soft sense. It is a direct operational risk. The degradation is cognitive before it is behavioral. Slower problem solving, weaker working memory, faster overwhelm when multiple alarms sound at once. An alarm goes off at 2 in the afternoon, after a poor night of sleep following 3 weeks of the same grinding routine, and the thought that forms is, I will deal with that after I eat something. On Earth, that thought is probably harmless. On Mars, the gap between now and after lunch might be the difference between catching a problem and missing it past the point of easy recovery. The tools available are limited. Some psychological training before departure, a few protocols, remote sessions with Earth psychologists, with the delay baked into every exchange, a small pharmaceutical kit. These help. They are not nothing, but the core environment, the isolation, the delay, the monotony, the confinement, does not go away. You manage it at best. At worst, it wears you down quietly for so long that the wearing itself becomes invisible. Just the baseline texture of life on Mars. This is where the most important reveal in this section lives. Assume for a moment that all the physical systems are holding. Enough oxygen, enough water, enough calories. The habitat is sealed and pressurized. The temperature is controlled. On paper, the mission is proceeding. But the human system may not be fine. If motivation collapses, maintenance slips. If the crew fractures into cliques, cooperation drops exactly at the moment alignment is most needed. If depression hits one or two key people, tasks are delayed, done carelessly, or skipped. If someone has become numb from months of the same stress, they take risks they should not take. If someone is terrified, they refuse necessary ones. The mission logic falls apart not from a rupture or a fire or a failed pump. It falls apart because the people running the mission stopped functioning as a coordinated whole. Entropy does not just hit machines, it hits teams. A fully supplied crew can still fail. That is the uncomfortable truth that no engineering checklist captures. Over hundreds of days, the will to inspect that same valve, log that same anomaly, clean that same filter for the 4th time this month, wears thin. Skip one check and nothing happens. Skip that kind of check 5 times across different systems, and something serious fails quietly in the background, days before anyone notices. The failure mode is not dramatic. It does not arrive with warning. It arrives from the direction of exhaustion and eroded discipline and a social environment that has been under strain for so long that the strain feels like normal. The brain that was your best survival tool is capable of becoming the weak link, and there is no sensor for that. What individual crews will actually experience over hundreds of days on Mars and how well they will manage it remains genuinely uncertain. The psychology of long-duration isolation in that specific environment has never been tested at that distance, with that delay, for that duration. We have analogs, we have simulations, we have the best psychological preparation that current science can design. Whether that is enough is a question that only a mission to Mars will actually answer. And that answer is still waiting. The human system is one more variable the mission depends on, and it is the one that was never fully calibrated in advance. Every other threat on this list requires the crew to respond correctly, quickly, and cooperatively, which means every other threat on this list depends on the crew being psychologically capable of doing that, day after day, for as long as the mission runs. The comms delay makes that weight heavier still, and what the delay means for every other practical decision the crew faces is something worth looking at directly. That weight has an exact measure. It is counted in minutes of radio delay, and it shapes every decision the crew makes from the first day on Mars to the last. The geometry is simple. At closest approach, Mars sits roughly 54 million kilometers from Earth. At its farthest, on the opposite side of the Sun, the gap stretches past 400 million kilometers. A radio signal, traveling at the speed of light, takes between 4 and 24 minutes to cross that distance one way. Ask a question, wait 4 minutes for it to arrive, wait another 4 minutes for the answer to come back. That is the best case. 8 minutes gone for a single exchange. At the far end, a round trip takes close to 50 minutes. It is like shouting across a canyon and waiting almost an hour to hear the echo. On Earth, that sounds like an inconvenience, a frustrating delay, a communication quirk to plan around. It is not an inconvenience. It is a structural transformation of every emergency the crew will face. Think about what suit failure looks like. A seal goes, pressure begins dropping inside the glove or at the helmet ring. The useful action window is not 20 minutes, it is not even 5. The sequence from breach to incapacitation moves in seconds to a couple of minutes, depending on where the failure occurs. There is no calling Houston and waiting for a response. By the time a signal reporting the emergency reaches Earth, the event is already resolved one way or the other. The specialists back home are not out of the loop because of indifference or slow bureaucracy. They are out of the loop because the physics of the solar system will not allow them in. They will hear what happened. They can analyze what went wrong, review the logs, talk to the survivors. They cannot change the outcome. The help that matters arrives only if it was already on Mars when the problem started. This breaks something fundamental about the model of spaceflight that came before. Apollo crews had mission control in their ears through every procedure. Numbers were read, cross-checked, called out in real time by a room full of engineers who had rehearsed every failure mode. Shuttle and ISS crews operate inside continuous monitoring. Flip the wrong switch and someone in a building in Houston sees a data spike and calls you within seconds. That architecture is not just a communication preference, it is the safety system. The real-time link is what makes the whole thing work. On Mars, that link is gone. Not weakened, not delayed to an annoying degree. Gone in any sense that matters when something goes wrong fast. What replaces it is everything the crew brought with them. Their training, their pre-loaded procedures, their understanding of the systems, and whatever they can improvise in the moment. Earth can still send checklists and software patches and updated decision trees during quiet periods. Engineers can review the previous day's logs overnight and flag anomalies. Doctors can suggest a treatment plan after studying the morning's medical readings. All of that is real, and none of it is nothing. But when a pressure number drifts unexpectedly and alarms light up, the only minds that can act on it in time are already standing in the room where it is happening. The culture of spaceflight shifts from remotely piloted to autonomous or dead. You must understand the failure modes of your systems not as a general familiarity, but as a working mechanic's knowledge. You troubleshoot under stress without a calm voice from a safe room walking you through the steps. You rely on what you rehearsed and what you can reason out. If you get it wrong, there is no one close enough to catch it. Then the data shifted. The delay is not the only problem with the data pipe. The link itself is not always available. High-gain antennas require precise pointing to maintain a connection. Relay orbiters in Martian orbit have line-of-sight constraints, and Mars rotates. Terrain blocks views. Earth, Mars, and the Sun periodically arrange themselves in configurations that degrade or cut the signal entirely. These are called comms windows and comms blackouts. During a window, the crew pushes data, syncs logs, uploads updated procedures, pulls new software. During a blackout, they get nothing. Not reduced information, nothing. A critical failure during a dead zone means the crew cannot even inform Earth there is a problem. Ground teams may not know anything is wrong until the next communications pass, by which time the crisis has either been resolved or it has not. Either way, they will learn about it after the fact. Even in the windows, complex technical problems move slowly. A software bug in a life support controller on Earth gets diagnosed by a team with full telemetry access, patched, tested, and deployed in a managed environment while the system runs under supervision. On Mars, the round trip for a diagnostic exchange runs hours. A patch has to be written, validated, transmitted, received, and uploaded while the crew monitors a misbehaving system they may only partially understand, waiting on a fix they cannot rush. This is not a hypothetical edge case. Software on systems that run continuously for a year will require updates. Hardware will behave unexpectedly. The time between noticing something wrong and having a confident response to it stretches from minutes on Earth to days on Mars. And all of that happens against a permanent background awareness that there is no one to call. Not really. Not in the time frame that the stress response cares about. That awareness does not stay in the background. It accumulates. Every decision carries more weight than it would back home. Shut this system down and lose a function for the next several hours, or let it keep running and risk a larger failure? Send someone out to inspect the antenna mount in marginal weather, or wait for better conditions and risk falling further behind? There is no supervisor to escalate to. You can write a report and send it to Earth and receive a thoughtful response, but that response will arrive long after the moment when it would have changed anything. In the moment, you are supervisor, specialist, and the person who goes out to tighten the bolt. Decision fatigue builds faster under those conditions. Over months, the combination of responsibility, delay, and the knowledge that every call is final skews judgment in predictable directions. Some crews go overcautious, avoiding reasonable risks, deferring necessary repairs because the cost of getting it wrong feels too high. Others go the other way, numbing to risk, taking shortcuts because the system has held so far, and the alternative is another exhausting deliberation with no good answer. Both failure modes are dangerous. One bad call without real-time backup can cascade into something the crew cannot recover from. Lag is not one problem among many. It is a force multiplier on every other problem this mission carries. A radiation spike, a water leak, a power fluctuation, a medical emergency. Each one is harder to manage when every emergency is effectively local. There is no cavalry arriving at the last second. There is no expert yelling the correct answer through an earpiece at the critical moment. The only people who can act in time are the ones already in the danger, working with whatever knowledge and resources they arrived with. A year is long enough that at least one serious crisis is likely. That is not pessimism. It is probability. And the chance that a small crew handles every one of those moments flawlessly, under accumulated fatigue, with degraded physical reserves, in the absence of real-time external support, is not high. The delay does not have to kill anyone directly. It just stretches every request for help until after the moment help would have done the most good. And lag is not the last weight this crew carries. What surrounds the habitat on every side adds another kind of pressure entirely. That pressure surrounds the crew on every side. And what fills most of their time inside it is not exploration. It is maintenance. Think about what you imagined when you pictured a Mars mission. Rover tracks across a red terrain. Samples sealed into collection tubes. Photographs of something no human eye has ever seen. That image is real. It is just not most of the picture. Most of the picture is a crew member wedged behind a rack of tanks in a cramped utility bay. Flashlight in one hand, checking a valve fitting for the 4th time this week. Inspecting the same panels. Cleaning dust from the same seals. Lubricating the same moving parts with specialized greases that behave unpredictably in thin, cold air. Swapping cartridges before they are fully spent because stretching them even slightly is not a risk you can afford. This is the maintenance tax. It is non-negotiable. Every pump, every filter, every cable, every valve, every circuit on that mission runs in conditions it was never truly designed for. Cold that stiffens materials, dust that infiltrates every gap, radiation that slowly degrades electronics from the inside, low pressure pulling at every seal. The hardware runs in all of this, continuously, for 12 months, and the hours required to keep it running come directly out of the hours available for everything else. On Earth, skipping a maintenance task costs you a slightly higher repair bill. You push it to next week. Someone else might catch it before it matters. On Mars, skipping one inspection for an extra hour of sleep can mean a pump fails weeks ahead of schedule, or a filter clogs at the worst possible moment. You will not see the connection when it happens. You will just see a red light and hear an alarm, already low on energy, already stretched thin, now managing a crisis that was quietly building since the morning you chose sleep over a routine check. The maintenance tax does not negotiate. It collects one way or another. But the reality was different. You can plan for the maintenance schedule. You cannot plan precisely for what will break. On Earth, replacement parts are a phone call and an overnight delivery. On Mars, overnight is 6 to 9 months. That is the interplanetary transfer time, assuming a launch window is even open when you need it. If the timing is wrong, the window closes and you wait longer. The parts you have are the parts you launched with, plus whatever limited fabrication your 3D printer can manage on-site. Spare part strategy becomes a high-stakes guessing game. Engineers on Earth made their best estimates. How many pumps? How many valve seals? How many sensor heads? How many bearings will fail under real Martian stress over a full year? Not lab test stress, not simulation stress. Real stress in real Martian conditions, with hardware accumulating where no test chamber fully replicates. If they guessed right, the spares hold. If they guessed slightly wrong on one bespoke component, the one with no standard equivalent, the one designed specifically for this mission, you are not swapping a part. You are redesigning a system under pressure, in a habitat with no proper workshop, with whatever materials you have at hand. You 3D print a bracket that was never in the original engineering drawings. You repurpose an off-the-shelf motor in a role it was not designed for. Or you cannibalize. You pull components from a less critical subsystem to keep a more critical one alive. robbing power hardware to patch life support, stripping a rover to fix a water processor. These trades are survivable sometimes. Each one narrows the margin for the next problem. The repairs themselves do not happen in ideal conditions. Some are inside the habitat, which sounds manageable until you are wedged into a space barely wide enough for your shoulders, reaching past a coolant line to access a fitting behind a structural support, with no room to turn your wrist in the direction the tool needs to go. Others are outside. Outside means a suit, thick gloves with limited tactile feedback, a helmet that restricts your peripheral vision and prevents you from leaning in closer to see, a body that cannot bend freely in a pressurized shell. Dropping a bolt on Earth is annoying. Dropping a small component into a critical pump on Mars can jam moving parts, damage impeller blades, or block flow in ways that are hard to access and harder to diagnose. The failure shows up later as an odd vibration, a slight drop in output, a reading that seems almost normal, but not quite. And now you are tearing hardware down further to find the cause, in a space too small for a proper disassembly, because a fastener fell the wrong way on a bad day. Sensor drift makes all of it harder. Materials under constant stress change slowly over time. Plastics deform. Loaded metals stretch by microscopic amounts. And sensors that were calibrated precisely in an Earth test chamber months before launch may now read a few percent off. A few percent sounds like a small number. It is not a small number when your safety margins are already tight. A pressure sensor reads nominal while pressure is slowly leaking. A flow meter reports that coolant is circulating while the actual flow has dropped below the safe threshold. A gas sensor underreports CO2 concentrations as its chemical sensitivity ages with use. Wait, that last one. You have already seen what happens when CO2 rises silently without triggering alarms. Sensor drift is a separate mechanism that can produce the same outcome. Not through equipment failure. Through calibration slippage that looks like normal operation the whole time. This is why believing every single reading without question is itself a failure mode. You need redundancy in information the same way you need redundancy in hardware. Two sensors measuring the same thing, so a discrepancy tells you one of them is drifting. Manual gauges to double-check digital readouts. Periodic calibration against known reference conditions. And a crew culture where a reading that conflicts with the system's behavior demands investigation, not reassurance. The answer, "It's probably fine," is not acceptable when the numbers say one thing and the machinery sounds like something else. Hidden leaks are the clearest example of why. A tiny crack behind a wall panel, an O-ring that thermal cycling and dust infiltration have slowly compromised. A joint tightened fractionally under specification on a rush day when the crew was already behind schedule. Air, water, or coolant slips out in amounts too small to trigger an alarm. The alarm threshold is calibrated for a real emergency. This is not a real emergency yet. It is a slow bleed. Over days, the tank level trends slightly downward. The pump behavior shifts almost imperceptibly. By the time the numbers are undeniably wrong, you have already lost a meaningful fraction of your buffer. The leak was always there. It was counting down before you noticed. Not dramatically, quietly, behind a panel you had not opened yet. Stretch all of this across 12 months. Thousands of temperature cycles, each one expanding and contracting the same bolts and seals and composite panels. Tens of thousands of pump hours on bearings that were rated for Earth conditions. Countless valve actuations, fan rotations, pressure cycling events. The number of components does not grow, but the number of opportunities for something to go wrong grows every day. Entropy does not care that this is the most ambitious engineering project in human history. Bearings wear, insulation breaks down, cable jackets develop hairline cracks, solder joints fatigue under vibration, connectors oxidize, fasteners loosen. Software surfaces edge case bugs it never encountered in testing because the test environment did not include 12 months of simultaneous thermal stress, radiation damage, and continuous operation. The most dangerous failures will not announce themselves. Not a sudden rupture, not a loud alarm, a tiny electrical arc inside a connector housing, slowly carbonizing the insulation around it, building toward a fire that starts inside a sealed habitat. A pump that sounds almost right, a barely audible chatter suggesting a bearing weeks from seizing. A pressure drift of a fraction of a percent per day, easy to attribute to normal variation, actually masking a leak that is approaching the threshold where the alarm finally sounds and you realize how long it has been counting. On Earth, a maintenance team with the right tools, the right parts, and rested judgment resets the clock. They swap the bearing before it seizes. They find the arc before it ignites. They catch the drift before it crosses the line. On Mars, only you and your crew can do that. Sleep-debted, physically worn, carrying the accumulated weight of months of isolation and high-stakes decisions. You are the maintenance team. There is no other maintenance team. The longer the mission runs, the more the odds shift. Not toward failure as a certainty, but toward failure as a probability that grows every week, tilted by hardware that has been operating past its comfortable design envelope and a crew that has been absorbing the cost of that continuously. Year 1 is a knife edge, not because landing on Mars is impossible, and not because the hardware is poorly designed. Because keeping every critical system ahead of entropy for a full Martian cycle, with no resupply and no outside repair team, requires a margin that started thin and gets thinner every day. And when something breaks in a way the crew cannot fix in time, the consequences do not stay in the mechanical domain. A hidden fault becoming a fire becomes a medical emergency. A slow water loss becoming a system failure becomes a nutrition crisis. The threads connect. Every worn component, every drifting sensor, every skipped inspection ties back eventually to the humans depending on all of it. Which component fails first, and whether the spares actually match what Mars demands of them, are questions no one on Earth or Mars can answer with certainty in advance. That uncertainty does not sit still. It accumulates quietly in every junction box and seal and fitting. Every day the mission continues. And the mission continues into terrain that adds one more variable the hardware cannot shield against at all. And when the failure finally lands not on a pump, but on a person, here is everything you have to meet it. On Earth, a serious medical event triggers a system. You call for help and the system arrives. Ambulance crews, emergency rooms, imaging suites, specialists, labs, blood banks, surgical theatres, intensive care units, thousands of square meters of infrastructure mobilized in minutes. That system has been built over generations, and it works so well that most people never stop to think about what it actually contains. On Mars, that system compresses into a few cabinets and a small equipment rack, maybe a compact ultrasound, a portable device for basic blood tests, a vital signs monitor, a portable ECG to read the heart's electrical activity, a laptop loaded with reference manuals and treatment protocols, and a limited supply of drugs carefully chosen for weight, painkillers, antibiotics, a handful of heart medications, some anti-anxiety medications, steroids, allergy treatments. That is the medical safety net for a crew of human beings living one of the most physically demanding lives ever attempted. No CT scanner, no MRI, no full chemistry lab, no sterilization suite, no blood bank, not a reduced version of an emergency room, a closet. The weight limits that strangle every other system strangle this one too. Every kilogram launched toward Mars costs more than almost anything else in the mission budget. So the medical kit is sized for the most likely scenarios, optimized for what fits, and then it is frozen. Whatever is in those bags on landing day is what exists for the entire mission. There is no restocking, there is no calling in a specialist. When the gap between what a situation needs and what those cabinets contain becomes visible, the crew fills that gap with improvisation and hope. And the situations that can make that gap visible are not rare. The habitat is a working environment. People move equipment constantly. They climb ladders. They work with heavy tools in a gravitational field that feels light but does not forgive inertia. A partial gravity misstep into a bulkhead edge. A shifting crate catching a hand. A piece of machinery moving unexpectedly and pinning someone. These are not imagined disasters. They are the texture of daily work in a confined, equipment-dense environment. Outside in a suit, the stakes climb higher. A stumble on uneven rock terrain can twist a knee badly, slam a back against a rover frame, bounce a helmet against a hard surface. Inside a pressurized suit, you cannot flex the way your body wants to when it senses impact. You cannot curl away from a fall the way instinct demands. The suit is rigid, the force goes straight in. Fractures, dislocations, spinal injuries, internal bleeding. None of these require a dramatic catastrophe. They require a bad day at the wrong moment. On Earth, serious trauma goes to surgery and the intensive care unit. The window for that response is measured in minutes, On Mars, evacuation to Earth is not measured in minutes. It is measured in months, and only if a return vehicle is ready and the orbital geometry allows a launch window. In practice, that means evacuation does not exist as a real option. If the crew cannot stabilize the injury inside the habitat with the tools in those cabinets, that is the end of the line for that person. The answer was stranger than expected. The threats that look most dramatic are not always the ones that end missions first. Small injuries matter enormously in a sealed environment. A cut from a sharp equipment edge, a scraped knee, a blister that opens inside a boot during EVA. On Earth, these are minor irritations, dealt with in seconds and forgotten. On Mars, the biological context is different. Radiation has been quietly suppressing immune function for months. Poor sleep and chronic stress have worn the body's defenses down. The habitat's closed-loop biology means microbes have fewer places to go, and surfaces in water systems, drains, and corners accumulate biofilms, thin biological films that harbor bacteria, if cleaning routines slip even slightly. Bacteria adapt quickly in that kind of environment. Some will develop resistance to one or more of the limited antibiotics in the medical kit. And here is the part that has no clean solution. With no full laboratory to culture a sample and run sensitivity tests, the crew is guessing. They consult the reference manual, they assess the symptoms, they make the best call they can with incomplete information. Guess wrong, and a routine skin infection can move into deeper tissue and then into the bloodstream. Sepsis, a full-body inflammatory response to systemic infection, requires aggressive fluid replacement, precise antibiotic targeting, and often intensive care monitoring. The Mars habitat offers limited fluids, imprecise antibiotic selection, no intensive care unit, no mechanical ventilation for a patient in critical respiratory decline. What is treatable on Earth becomes genuinely life-threatening there. The hidden conditions add another layer. Crews are screened heavily before selection, but no screening process is perfect. A mild heart rhythm abnormality that never appeared in any previous examination. A genetic tendency toward blood clots that only surfaces under the specific combination of dehydration and reduced physical activity. A mood disorder managed well in normal life that breaks through under isolation, confinement, and relentless workload. On Earth, an arrhythmia gets a cardiologist, a full diagnostic workup, adjusted medications, and possibly a procedure. On Mars, the crew has a small ECG, a few relevant drugs, and a reference guide. They improvise, they watch, they hope the condition stays manageable. For mental health, there may be some medication and remote consultations with Earth-based psychologists, but those consultations arrive after a delay measured in minutes or tens of minutes each way, and the core stresses, the isolation, the confinement, the weight of every decision do not go away because a session ended. And then there is the question no mission planner wants to linger on too long. What happens if the medic goes down? The crew's one person with serious medical training is just as exposed to radiation as everyone else, just as likely to slip on a ladder, inhale too much dust, develop a hidden condition, or simply get sick. If that person becomes a patient instead of a provider, the crew falls back on whoever has the next best training. A few courses, some simulation time, real commitment but a fraction of the depth. That is the difference between a high-end hospital and a small first aid tent. And everyone in the tent is hoping nothing complicated walks through the door. One bad day can be enough to end a mission that is otherwise working. Think about appendicitis. On Earth, it is a surgical emergency handled within hours and routinely survived. On Mars, the crew faces a decision with no good options. Attempt surgery with limited instruments and a crew member who is not a surgeon. Or manage with antibiotics and monitor closely, hoping the appendix does not rupture. If it does rupture, the result is abdominal infection requiring drainage and aggressive treatment, in conditions that offer a bunk, a few monitors, and whatever antibiotics remain. Think about a pulmonary embolism, a blood clot that travels to the lungs and blocks circulation. Sudden chest pain, shortness of breath, possible collapse. Diagnosis requires imaging the Mars kit does not have. Treatment requires specific anticoagulant drugs that may or may not be in the cabinet. And if that crew member dies, and if that person was the primary engineer, the life support specialist, or the only qualified pilot, the mission arithmetic changes immediately. Fewer hands, higher workload per remaining person, less margin for everything else, higher probability that the next problem also goes badly. The same cascade applies to heart attack, stroke, severe systemic infection, or a psychiatric break where a crew member loses touch with reality or becomes a danger to themselves or others. On Earth, there are layers of response. On Mars, there is one layer. Your crew, in that moment, with what is in those cabinets. The verdict is not that medical emergencies make Mars impossible. The verdict is that they represent a category of risk where the failure mode is not engineering, it is the completeness of a safety net that weight limits forced into a closet. A single major medical event hitting the wrong person at the wrong moment, during a dust storm, during a power issue, during a maintenance backlog, can drop operational capacity below the threshold needed to safely run the base. Not because the planet overwhelmed the mission, because the mission was running a full human body and mind support system, with tools designed for minimum mass, not redundancy. And while a crew is focused on an injured crewmate, the ground beneath their feet is adding variables of its own. The floor has been moving the whole time, every eye in the habitat focused on the patient, monitoring vitals, rotating watches, running through the small drug formulary, looking for something that fits. That kind of crisis compresses attention into a single point. And while that happens, the base itself continues to exist, inside a planetary environment that does not pause for medical emergencies. The ground under those landing pads does not wait for a quieter week. Most people picture the Martian surface as geologically dead, cold, still, locked. A world that stopped doing anything interesting billions of years ago. That assumption is wrong. Mars still moves. The InSight lander confirmed it. Mars quakes are real, and they register around magnitude 4 to 5 on the Richter scale. Not the kind of event that collapses buildings, but enough to shake a habitat, rattle mounted equipment, knock unsecured tools off surfaces, and drive sudden stress into every support frame and every bolted joint the base sits on. One event like that is manageable. The engineering accounts for occasional loading. But 10 to 20 such events across a single year, spread unevenly, arriving without warning, are a different problem entirely. Here is where the ground becomes dangerous. Not the shaking itself, what the shaking does to what is underneath. Martian regolith, the loose fragmented layer the base is anchored into, is not uniform. It looks flat. It looks consistent. It can hide voids below the surface, ice pockets at depth, weak layers that behave normally under static weight, but respond differently under repeated dynamic loading. Every time a Marsquake rolls through, that layer compacts a little more in some places, shears slightly in others. Over months, one landing pad sinks a few millimeters farther than its neighbor. One support frame twists a fraction of a degree. The whole module tilts, not dramatically, just enough. A few degrees sounds like nothing, but systems were built to a specification that assumed level. Tilt a module and fluid flow changes. Tanks read wrong because level sensors are now measuring off-axis. Doors that once sealed cleanly now bind on one side and gap on the other. Structural load that was once distributed evenly across the frame shifts onto 2 or 3 bearing points. Pipe connections that were running parallel to their fittings now carry lateral tension they were never designed for. Seals that were flat against their mating surfaces now press unevenly, beginning the slow work of developing a leak path. None of this announces itself. It arrives quietly across weeks, until one day a door sticks and someone forces it, and the habit of forcing it is established, and the seal degrades faster from that point forward. But something was wrong. You can pick a flat, open site far from crater walls and canyon rims, away from any obvious slope, and still face settlement, because flat ground hides its problems underground. A habitat module weighs tens of tons. Mars gravity reduces that felt weight, but the stress concentrated on landing pads and foundation plates is still significant. Over months, that weight compacts soil unevenly. One pad happens to sit over a slightly less dense region and sinks more than the others. A buried void, a hollow left by ancient ice that sublimated away long ago, collapses under a critical support. The heated interior of the habitat raises ground temperature slightly in contact zones, thawing frozen ground that then refreezes differently when the heating cycles down, changing the support geometry that was there the day before. The floor tilts half a degree, then another. A door that almost sealed last week no longer seals at all. A gap appears at the base of an interior wall that was flush on arrival. On Earth, This is a foundation problem. You call structural engineers, you run ground-penetrating surveys, you pour new concrete, jack and relevel, rebuild the support. On Mars, you are the structural engineer, whether or not that is in your file. With a limited set of survey tools, minimal construction equipment, and almost no margin to isolate and shut down a module for weeks while you rebuild what is underneath it. And the ground is not the only thing applying force. Global dust storms on Mars last week's. Wind speeds during major storms reach 20 to 30 meters per second, roughly 45 to 65 miles per hour. The atmosphere is thin enough that the force on large objects is less than you would feel at the same wind speed on Earth, but not zero. Solar panels, antennas, exterior tanks, surface structures all experience constant cyclic loading as gusts and eddies flex their mounts, rock their supports, and push dust into every exposed joint and gap. Anchors driven into regolith experience back and forth forces that slowly work them loose, especially as the surrounding soil compacts and erodes around them. Brackets fatigue. Fasteners that were tight at landing gradually back out under vibration or develop micro cracks from repeated bending. The dust itself acts like fine sandpaper on every exposed mechanical surface, wearing seals, abrading cable jackets, grinding into pivot points faster than any Earth-based lab test suggested was possible. A single storm is a known load. The structure was designed to survive it, but a sequence of storms across a year, each one loading fatigued mounts, each one driving slightly more dust into joints that were already slightly compromised, each one vibrating anchors that were already slightly loose, is a different calculation than the one the designers ran. The compromised shell verdict arrives quietly. From outside, the habitat looks intact. The pressure hull is there. The modules are connected. The visible structure shows no obvious damage. But inside, a base that absorbed 10 Marsquakes across 8 months, settled unevenly under the weight of its own modules, and endured weeks of storm loading on already fatigued mounts, can already be a different structure than the one that landed. Air leaks at joints that no longer seat correctly, misaligned hatches that cannot seal under pressure, pipes carrying tension toward the point where they rupture, cabling stretched across a shifted conduit until insulation cracks. The structure did not fail dramatically. It drifted into a compromised state across hundreds of quiet hours, while the crew was focused on everything else. The ground was never just there. It was always another system that had to be understood and managed. A base that treated it as a static platform, that assumed site selection solved the problem permanently, that did not account for years of seismic loading, slow settlement, and cyclic storm forces on anchors and mounts, discovers its optimism over the course of year 1. And when the ground finally collects on that debt, the first systems it attacks are the ones that keep the lights on. Power is what the lights on means. The ground attacks it first because power is the thread the whole tower hangs from. Cut it enough and the air goes wrong, the heat goes wrong, the water slows, the food dims, the comms narrow. Not a cascade of separate problems. One cascade, one thread, pulled from the bottom. The numbers explain why it is so exposed. At the top of Earth's atmosphere, sunlight arrives carrying roughly 1,360 watts per square meter. At the top of Mars's atmosphere, that same sunlight carries about 590 watts per square meter, less than half. And that is before the light passes through Martian air and the dust that is always in it, before it reaches the panels, before any efficiency loss in the panels themselves. On a clear Martian day, you can design around the reduced flux. You angle the arrays, you oversize them, you add sun tracking. But Mars does not cooperate with averages. A serious dust storm can cut solar output by 50 to 90%. Not a dip. Not a difficult week. A your entire energy plan just broke event. If the batteries are sized for an average sunny day plus a modest buffer, a storm that runs for weeks does not care. You watch the charge ramp down while the panels give back a trickle. You can suit up and go out to clean them. But during a big storm, the air is full of fine particles, and the light is dim and reddish from horizon to horizon. So you burn stored energy and accept physical risk just to recover a small fraction of what you have lost. Many mission plans reach for nuclear to solve this. Compact fission reactors, steady kilowatts around the clock, indifferent to dust and sunlight and the tilt of winter. On paper, the reactor closes the gap. It keeps the loop running through storms that would otherwise hollow out every battery bank. That part is real. The picture did not hold. The reactor that solves the storm problem arrives, carrying its own set of failure modes that can end the mission without anyone dying immediately. The shielding is heavy. The cooling system, the pumps and coolant loops and radiator arrays that carry waste heat away from the core, is itself exposed to Mars conditions. Temperature cycling attacks the joints. Dust gets into moving parts. A coolant leak in a reactor circuit is not a lost efficiency number. It is possible overheating, automatic shutdowns, core damage. And a failed reactor control system means managing a high-consequence machine with no easy evacuation route, a thin medical kit, and whatever specialist knowledge the crew brought with them. A radiological emergency near your only safe habitat can make that habitat suspect. Not destroy it in a moment. Make it suspect. Make everything downrange of the incident a question you cannot fully answer. The mission can end that way too. Quietly, with no single catastrophic event to point at. Storage adds another layer. Even with solar and nuclear combined, you still need battery banks to smooth demand, cover generation gaps, and keep critical systems alive if a generator trips. Batteries are not passive. They age. Cold cuts their effective capacity. Heat speeds their degradation. And when a battery bank fails badly, the cells can go into thermal runaway, overheating, venting gas, catching fire, heating the neighboring cells until they join. Scale a car battery fire to a habitat-level bank in a sealed, pressurized structure with limited air volume and no door to the outside that opens onto safety. Fire in that space is not a lesser threat than the vacuum outside. It is a different version of the same threat. Suppressing it means taking a whole power block offline. If that block was the main storm buffer, the cushion between the crew and a blackout is gone. The margin the crew is working inside is already narrow. The power budget covers life support, heating, cooling, water processing, oxygen generation, CO2 scrubbing, lighting, greenhouses, rovers, comms, labs, computers. Add it all up. Build in reasonable efficiencies, and a well-designed system might carry a 10 to 20% margin over expected peak load. That margin absorbs surprises. A colder night, a dustier season, extra pump time from a clogging filter, more greenhouse lighting for crops that are underperforming, a new insulation crack, bleeding heat into the regolith. When the margin is small, small things push past it. Once the system is in deficit, the crew makes sacrifices. Temperature turned down, lights dimmed, rover trips delayed, non-essential experiments suspended. Then, in a real crunch, secondary life support backups powered down to save kilowatts. Each sacrifice buys short-term time and raises long-term risk. Power down one redundant CO2 scrubber to save a few watts, planning to alternate units, and then a storm cuts solar by 80% instead of 50%. Now you're running on a single scrubber with no spare. Reduce greenhouse lighting hours, and the next harvest comes in smaller, pushing the food margin closer to deficit. Lower the habitat temperature to the edge of comfort, and the machines, the pipes, the lubricants, the seals, all run colder than they were designed for. The probability of their failure rises. That is the deficit spiral. Not a single decision that dooms the mission. A sequence of reasonable-seeming decisions that each narrow the margin a little further until there is nothing left to give. When power underperforms by even a modest fraction, the whole integrated system feels it in sequence. Heat drops and pipes flirt with freezing. Life support chooses between full performance and energy savings. Water extraction slows. Food production loses light hours. Comms windows tighten. Maintenance teams get less time with powered tools and more hours of manual work, making them slower and more worn. All of that amplifies every other threat. The radiation still coming, the bones still losing density, the dust still settling on panels and into joints. You do not just lose power. You lose the ability to keep all the other plates spinning at once. Temperature, atmosphere, water, and food are chained to energy output. When power stumbles, they begin to fall in sequence. That is the mechanical shape of cumulative failure. But there is one more system, and you cannot put a sensor on it. The people running all the machines are themselves a system, and they are running as close to their own margins as the hardware. An outpost of 4 to 8 people works long hours in a small pressurized volume. You hear each other's footsteps, breathing, keyboard clicks. You know who snores, who taps fingers, who mutters when something will not work. Privacy is thin. A curtain, headphones, a corner claimed by convention. You cannot go outside to reset. Outside requires a suit, a safety check, a buddy, a procedure. So every interaction carries extra weight. A joke that lands badly does not disappear into a crowd. A tense conversation over a procedure does not fade. You see that person at the next meal, at the next shift, in the corridor you both have to use. Small annoyances stack. How someone eats, how they leave tools, how they respond under pressure. And in a sealed box millions of kilometers from anywhere else, they start to feel permanent. Meanwhile, the stakes of cooperation are absolute. You must trust that the person checking your suit seals was not rushing, that the night shift crew member will answer alarms correctly, that if you are hurt, the crew treats you even at cost to themselves. Mutual trust is not a nice quality in this environment. It is load-bearing infrastructure. It tears more easily than steel. A chain of command, a commander, system leads, a medic for health decisions, adds structure but also complexity. Earth is still there, but every message takes roughly 20 minutes each way at mid-mission distances. Does the commander have final say in an emergency? Wait for mission control on the big calls? Decide by consensus? Picture a borderline case. A storm builds. A power anomaly appears. The crew can send someone outside now to secure a panel, or wait and hope. One person says, "Go now. We cannot risk the panel." Another says conditions are too marginal. The EVA carries more risk than the panel loss. The commander must choose. Maybe Earth sent guidance last week about being more cautious with EVAs in storm conditions. Whose risk tolerance wins? That question does not have a clean answer. And Mars does not slow down while the crew debates it. If people feel leadership is reckless, they drag their feet. If they feel it is overcautious, they start cutting corners on their own. A divided crew may not execute critical procedures on time, or may half-execute while the disagreement persists. The planet gains ground either way. Overwork is the quieter fracture. Long days, often longer than planned, because something always needs attention. Maintenance, science, construction, reporting, drills, actual emergencies. Sleep gets squeezed. Breaks shrink. Chronic overwork changes people in ways that do not announce themselves. Attention slips. Patience wears thin. Someone calm and precise in training starts snapping or zoning out. Another skips non-urgent checks because they cannot face one more checklist. Burnout is not a dramatic collapse. It is a slow drop in care. I will log it later. That reading is probably a sensor glitch. The protocol says 2 people, but I will do this alone. Each is a tiny cut in the safety margin. Aggregated across weeks and a full crew, they become the background condition under which a missed filter change or a delayed inspection becomes the origin point of a failure that looks unrelated. And then there are the questions that have no good answers at all. If a crop failure and a water shortage force stricter rationing, who gets priority for calories, for medical treatment, for oxygen? A severely injured crew member whose care consumes a large share of supplies, power, and crew time, with uncertain odds of recovery. Do you pour everything in, knowing it may compromise the rest? If they can no longer work, do they receive the same share of limited resources? What if the patient is the only qualified specialist in a domain the mission depends on? These are not hypothetical ethics problems. They are real-time decisions that the crew must make and then live with inside a confined space, looking at the outcome every day. Guilt and resentment and second-guessing can move through a small group like a slow toxin. And if a mental health crisis makes someone a danger to the mission, restraining or sedating a crew member with no external oversight, no review board, no institutional buffer, is an ethical weight that can permanently alter every relationship on board. Those questions stay open. There is no procedure that resolves them in advance. Pull all of it together, and the final failure mode is human nature. Not because people are weak, because people respond to stress, fear, exhaustion, and grief per their personalities and histories, not per physics and statistics. The air recycler and the reactor wear out on predictable curves. People do not. If trust erodes, procedures become optional. People stop double-checking each other's work, offended by being checked, or no longer believing the check will be done right. Corners get cut to avoid arguments. Information gets filtered, a mistake downplayed to avoid blame, symptoms hidden to avoid being pulled off duty. And Mars does not need to do anything dramatic against a crew in that condition. It just keeps doing what it already does. Stay cold, stay dry, keep the radiation coming, keep the dust settling, let the equipment age and the bones thin. A socially fractured crew is less able to respond, less willing to cooperate, and less likely to catch problems early. The planet wins almost by default. That is the thesis beneath everything. You do not fail year one because of a single catastrophic event. You fail because a long chain of small stresses, physical, technical, psychological, social, lines up across enough months, and most of those stresses run through people. If the crew cannot hold together, the best engineering extends the timeline, but does not change the outcome. Surviving a year on Mars is not about tougher suits, thicker walls, or smarter software alone. It is about designing for human bodies, human minds, and human groups in a place that is specifically, comprehensively, indifferently suited to finding every weak spot at once. The atmosphere does not care. The ground does not care. The radiation does not care. Mars only has to sit there and wait. And right now, that is exactly what it is doing.